Okay, so start recording now. So I wanted to talk about state functions and path-dependent functions. So state functions are functions that depend only on the state of the system. And a lot of them are really obvious, like temperature or pressure or volume. Those depend on the state of the system. The temperature of the system is the temperature state. The volume is how big it is. There's a couple of properties of state functions that are important. One is that they only depend on the initial and final states of the system. So if something changes, so say the temperature changes by 10 degrees, the temperature, the delta T is 10. Now I know that might sound silly, but anything could have happened in between that. So if you start at 1 degree and you get to 11 degrees, delta T is 10. You don't know in between whether it went up to 40 and down to minus 20 and then here. All you know is the initial was 1, the final was 11, so the change was 10. So state functions are like blinder functions. You look at the initial state, you put the blinders on, and you open up and look at the final state, and all you need to do to get the change is take the final value minus the initial value, even though stuff happened in the middle. Now you might say, well, that's obvious, and it is to a certain extent, but energy is a state function. So energy is something you can have, and if I talk about my energy right now, and my energy at the beginning of the day, the change in energy is my energy now, final, minus initial, the energy at the beginning of the day. Even though I was up and downstairs and I maybe ate something, blah, 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 I took in and all kinds of energy went in and out, but my change in energy is just my energy now minus my energy then. So that's a state function. Depends on my state right now and the state back then, but nothing in between. But there's other things that do depend on the path. That is, they depend on what you actually did. And those are called path-dependent functions, and they're things like work and heat. Those things matter what you did. But they both have the same units of energy. So we measure work and heat in joules and energy in joules. So it's sometimes confusing, am I talking about a state function or am I talking about heat or work? So an easy way to think about it is, let's talk about this soup can. So I can do work to crush the soup can. I can put it on the floor and I can crush it. Okay, that's work to crush the can. I did 1 soup can's worth of work crushing it. Another way I could crush the can is instead of crushing it directly, I could do the work on me, my body, step up a step on a ladder, and then at any time, I can jump off the ladder and crush the can. I've given myself 1 can's worth of energy by doing 1 can's worth of work on me by lifting me up enough to crush the can. So when I did the work, I got 1 can's worth of potential energy. And that's, I have the potential now to crush the can whenever I want. That's why we call it potential energy. I can potentially crush the can, but I don't have to. I can do it anytime because I got the energy now. I did the work, I went up 1 step. So I could go up another step on a ladder and get 2 soup cans worth of energy. So the work is a soup can worth of energy. It gets stored in me as a soup can worth of energy. Every soup can of work I did gave me a soup can worth of energy. It was 1 to 1. But there was another way to get to the top of the ladder. For instance, I could have started over here, walked over here, and then walked up the ladder. And if I had the blinder function on, as far as I was concerned, as I was at the bottom of the ladder, now I'm at the top of the ladder. So energy-wise, all it looks like is I've got my 2 soup cans. But it actually took me work to walk over to the ladder. So the total work to crush the soup can, if I jump down and crush the soup can, is bigger because I had to do this walking over here. So the work done to get up the ladder and crush the can is different than the energy change. The energy was just from up here, jumping down to crush, because the work that I was doing walking around didn't increase my energy. So the walking around didn't help because that wasn't raising me. It's gravitational potential energy that I'm getting, right? If I get higher above the ground, I have more soup cans worth of energy, but walking around doesn't give me any more. Okay? So that's actually interesting enough to plot out. So let's just plot that out. Let's say I started here, and I walked around to here, and then I climbed the ladder here, and I climbed 2 soup cans up the ladder, okay? So by climbing 2 soup cans up, I got some potential energy. But I went there in 2 steps. I went here, so I went path 1 and then path 2. Each of those had work associated with them, but only one of them, path 2, gave me potential energy. So my total energy change, potential energy change, is, I could calculate it from energy change is work plus heat. There's no heat at all here. All I'm doing is work. So the total energy change is the work, and I can say the energy change along path 1 is 0. I did work, but the energy change is 0. The energy change along path 2 is the work I did to go up the hill. So here's a good way to look at it. This is work along the x direction. This is work, I can erase that. Go back to pen, I don't know what I'm doing here. This is work along the y direction. Work along the y direction gets me energy. Work along the x direction didn't. Okay? So work is what you call a path-dependent function. Work depends on the path. The energy change doesn't. But sometimes, some kinds of work are state functions, in that any work you do in the y direction is exactly equal to a state function. So if you can set a variable equal to a state function, then it must be a state function too. So there was a lot of work done. The work in the y direction is a state function. Work in the x direction is not.
So we just don't consider the work in the x direction?
If you want to know the total work done for the system, then you have to add up work x plus work y. If you want to know the energy change, only work y went into changing the energy. So the energy change to get from here to here, let's say I went on that path. The energy change from getting from here to here is the same whether I went this path or this path. That energy change is the same. The work is different for those 2 paths. And you know this, if you go up a hill straight up the hill, that's work. But if you go up a hill walking around and around and around and around in a circle, that's a different amount of work. But you're still at the top of the hill. You're still the same potential energy. The potential energy difference is the same. Okay? So work and heat are not state functions, but sometimes components of them are. Okay? So let's look at it for, let's do the same thing for gases. So now I'm going to plot P and V. Here we were just plotting essentially X and Y, right? So I can do P and V for gases, and I can be a little anal. And, oh boy, I have to change myself back to the pen. Plot P and V, And now I say, well, what if I do a change here? What if I wanted to go change an energy from here to here? This is temperature T1. This is temperature T2. Now, I could get there going straight up between the two, but I want to find the energy change for doing those. The energy change doesn't matter what path I'm taking. The work and the heat would, but the energy doesn't. So I could go there 2 steps like this one. I could go this path first. So this will be path 1, and then this path, path 2. Okay? And then to get the total energy change, add up the energy changes for each path. Okay? So the energy change for path 1 is what? Well, I've drawn the path 1 very cleverly. This path, at every point along this path, the pressure times the volume is a constant. Okay? So that's a parabola. E times V is a constant. Okay? So, and you know what that constant is? It's R times T. PV equals nRT. Just the gas law. PV equals nRT. I shouldn't have used a K there. That's not ultimate constant. That's just a constant. So this PV is equal to nRT, and T is the constant. Along every point on this line, the temperature is the same because the product of the pressure and the volume are the same. So when you look at PV equals nRT, if P times V is a constant, that constant is the temperature. So the temperature is the same for every single one of those points. So along there, the temperature did not change. Okay, so it's T1, it's also the gas is at temperature T1 up here too. So for gases, you know that the energy of a gas is 3/2 RT. If the temperature doesn't change, the energy doesn't change. Here, delta T is 0. In fact, that's a neat part of gases. A real gas, an ideal gas, the energy is the temperature, essentially. You cannot change the energy without changing the temperature. The energy is 3RT. If the temperature changes by a degree, the energy had to change. They're just linked together. If the temperature doesn't change, that gas has the same amount of energy. So this is 0, that path 1, the energy of the gas didn't change because the temperature didn't change. Gases are transparent in that way. They can't change their energy without telling you. Their temperature has to change. If gas is at 10 degrees, that has more energy than a gas at 5 degrees. And it's absolutely linear. So gases are kind of easier to think about in terms of energy. So this, going here, path 1, that's just like this path here. You went along a path, but the energy didn't change. So what about the other path now? I'm going to do path 2. So the energy, change in energy along path 2. And now I'll just say it's Q plus W, because that's what energy is. In order to change the energy of a system, you have to do some work or add some heat. You can add or subtract heat. You can take heat out or put it in. You can do work or have work done on the system. Those are the two things that change the energy. So here, the second path, in fact, I'm going to, instead of 2, I'm going to call that sub P, because this was a constant temperature path. Along this path,
Constant pressure.
it's constant pressure path. And that's obvious because it's just horizontal pressure convention. So the constant pressure work and the constant pressure heat are what I have to add up. Here, it was the constant temperature work and the constant temperature heat. And it turns out those balance each other. One's the opposite of the other. So you get 0. So I can write down then that delta E sub P is QP, which I don't know, but work for a gas, we do know. It's minus P delta V. So this work part is plus, actually it's minus P delta V. We found that. Ink. Minus P delta V. Okay? Now I'm going to do something. I'm just going to rearrange this. So that means the constant pressure heat evolved is, I'm just going to bring the delta E sub P plus P delta V. Okay? So now I've done something kind of profound. The same thing I ended up doing over here. I expressed the heat in terms of only state functions. So now the heat, which is not a state function, but I've expressed it in terms of state functions. Energy is a state function. Pressure is a state function. Yes.
Okay.
So these are all blinder functions, state functions. And if I can express the constant pressure heat as state functions, then this must be a state function. That's the same thing we said over here. The y component of the work is a state function. The x doesn't help you. Same thing over here. The pressure component of the heat is a state function, but the temperature component of the heat was not. So this thing is a state function, the constant pressure heat of a system. So if something lets heat out or absorbs heat under constant pressure, that's a state function. And it's handy in the lab because we do things at constant pressure in the lab. So if you measure heat coming in or out at constant pressure, it's handy to know that that's a state function. So you don't actually have to know how the heat got in or anything. All you have to do is measure the initial and final states, and you get the change. So you don't have to keep track of anything to get the change. So it's so important that we give the constant pressure heat a big capital letter state function thing. And we actually use H because it's kind of like heat. But we don't call it heat, we call it enthalpy. So the enthalpy of a system is the constant pressure heat evolves in the system. This is a state function, and that's why, this is why we define it as a state function. This is easy to measure. It's the heat evolved with constant pressure in the laboratory. We can measure that. But it's a state function, so we can use it to compare to other things.
This is just making our lives easier.
Yeah, you define H. E in general is kind of hard to measure.
Yeah.
H is related to it very closely, but it's easy to measure because it's the constant pressure heat. Okay, that's it. I just wanted to show you that. So I'm going to stop the recording, and we're going to save that, and we're going to try and make a learning bite out of it later.
That was cool.
Stop video. How do I stop? Oh, stop recording.